Hello, it's me, Mr. Schnitzius again, saying hello to all you wonderful 80-minute Math Pascal students out there. We hope that you are safe and healthy, that you're getting outside and staying a safe distance away from people, but getting into a routine, getting into a rhythm with your other classes. This video is to show you some basics about inverse trigonometric functions that are going to help you for your inverse trig practice assignment. So this is going to still be built off of the unit circle, and we're going to use it to work backwards to get to the point where we can solve trigonometric equations where you have the sine, cosine, or tangent of a certain angle equals a value, and you're able to figure out what that angle is. So that's where we're headed. Let's get started with your graphs of inverse trigonometric functions notes. That looks like this. So our first inverse function that we're going to work through is going to be the inverse function for sine. So I've already filled in here the x and y values for the sine of x parent function. This is all straight from the unit circle. We could see what the starting point would be from an x value of 0, the sine value is 0. So we're going backwards, negative pi over 6, negative pi over 4, negative pi over 3, negative pi over 2. And the corresponding sine values for each of those angles as our y values. So we're going from a y value of 0, and then we're descending down to our minimum value of -1 right here. We've got these values as decimals also. So the sine of negative pi over 4 is negative root 2 over 2. That's the exact answer, but we want that as a decimal, negative 0.707. The sine of negative pi over 3 is negative square root of 3 over 2, but we want that as a decimal, negative 0.866. So these are the values down in quadrant 4. We're also starting at 0, 0 and going counterclockwise into quadrant 1. So sine of pi over 6 is 1/2, sine of pi over 4 is root 2 over 2, sine of pi over 3 is root 3 over 2, and then we're going to stop at sine of pi over 2 is 1. Now, you might ask yourself, why are we not doing a full period? Why do we only have quadrant 4 values of sine here and quadrant 1 values of sine here? Well, the reason is we are going to calculate the inverse sine function. So here's our original function, y equals sine of x. We're going to try to graph or get some values in a table for the function y equals the inverse sine of x. What we know about inverse functions, we could look at a graph and we would see that the original function and the inverse function are reflections over the line y equals x. But in a table, it's a little bit easier to see when you have an inverse function. All you have to do is simply switch the x value and the y value. So we're going to take each of these ordered pairs in this parent function table. We're going to reverse them. Reverse, reverse. So our original y value is -1. The x value here is going to be -1. The y value is going to be negative pi over 2. The original x value was negative pi over 3, so we're going to have negative pi over 3 as our y value over here, and our x value is going to be negative 0.866. And we're going to keep doing this, flip-flopping our x and y values. Zero, 0, that's pretty easy. Those stay the same. Now, we're going to pause real quick and we're going to think, how do we know that this table over here represents a function? Remember, the definition of a function is each x value maps to a unique y value. Another way of saying that is each input maps to only one output. The goofy example that Algebra 1 teachers like to use a lot and that I've used in the past is if your x values are the buttons on the Coke machine and the y values are the drinks that come out. If you have one button that matches up with Coca-Cola and also Dr. Pepper, you're going to hit the button and you're not going to know what's going to come out. That's a real problem, right? So you can see that each of these x values represents or is mapped to a unique y value. And you can just see that because none of the x values repeat. So that's why we're only using these x values when we're doing the table for y equals the inverse sine of x from -1 to 1. Because if we extended this original y equals sine of x table into quadrants 2 and 3, then we would, when we did the reverse, when we made the inverse function, we would end up with the same x value matching up with more than one y value. That would be a big problem, and we do not want that. So we're going to graph what the function y equals the inverse sine of x looks like. And this is just coming from taking these x values and plotting them with these y values. So the first one that we have there is when x is -1, we've got a y value of -pi/2. And we can see that when x is -0.866, the y value is -pi/3. And then at -0.707, so just a little bit closer to -0.8, we're going to have a y value of pi/4. That's going to be here in between -pi/6 and -pi/3. That's -pi/4. We also got when x is -0.5, y is -pi/6. Let's see, I need to scoot that point further to the left. There we go. That's -0.8, that's -0.4, so that's -0.707. All right, and then here we're gonna skip back to when x is 0, y is 0. So this is gonna give us a nice smooth curve about like so. And now we can do our quadrant 1 values when x is 0.5, y is pi/6. When x is 0.707, y is pi/4. When x is 0.866, y is pi/3. And when x is 1, y is pi/2. So this should look like a sinusoidal graph rotated, okay? So instead of the original y equals sine of x function saying, okay, when I have a certain angle, what is the sine value? This is telling me the reverse of that. It's saying, when I have a certain sine value, when sine is -1, what angle am I using? Well, I'm using the angle -pi/2. I'm on the negative y-axis. When it's easier to see this one, okay, that's 0.5. When the answer to the sine of x is 0.5, what angle have I been finding the sine value of? Well, that's when the angle is pi/6. Sine of pi/6 is 1/2. So we're going to look at what the domain and what the range are for the graph of y equals the inverse sine of x. That domain, the lowest x value is -1. The highest x value is +1. Since we are allowed to take on those x values, we're going to use these braces right here. This is we can use any x value or any angle for, or any value for sine in between -1 and +1 inclusive. The range, the answer to this is going to tell us when we know what the sine value is, what is the angle that we were plugging into the sine function. So the range that we're using is anything from -π/2 up to +π/2. We are allowed to use those angles, so we're going to use these braces right here. So that's your domain and range for the graph of y equals the inverse sine of x. So we're going to do the same thing now for the inverse cosine of x. These values come straight from the unit circle. What's the cosine of 0? 1. What's the cosine of π/6? √3/2. What's the cosine of π/3? 1/2. So these are our cosine values in quadrant 1. And then for the cosine of x, and over here on the right-hand table, the inverse cosine of x, we're actually going to go into quadrant 2. So cosine of 2π/3 is -1/2. Cosine of 3π/4 is -√2/2. Cosine of 5π/6 is -√3/2. Cosine of pi is -1. So just like we did when we were creating the table for the inverse sine of x, to do an inverse function, to use our parent function table to make the table for the inverse cosine of x, we're just going to reverse the x and y values. 0, 1 goes to 1, 0. π/6 √3/2 goes to √3/2, that's 0.866. π/6. π/4, 0.707 goes to 0.707 π/4. The cosine of π/3 is 1/2. So when we do the inverse cosine, that gives us the ordered pair 0.5 π/3. The cosine of π/2 is 0. So in the inverse table, that's going to give us 0 π/2. And now we're going to do the quadrant 2 values. We're just going to switch around x and y. So now in the inverse table, now the inputs are, these are values of cosine. If cosine is 0.707, if cosine is the square root of 2/2, that's what we're inputting into our function. What we're going to get out of this function is, oh, your cosine value is square root of 2/2. That means that the angle you were thinking about is π/4. So let's go ahead and graph that function. So we can see that and notice that the scale is different here, right? We only have positive y values that we're using. So when x is 1, y is 0. When x is 0.866, y is π/6. When x is 0.707, y is π/4. When x is 0.5, y is π/3. When x is 0, y is π/2. So we're going to make that sinusoidal curve like so. All right, now we're going to keep going into the negative values for x. X is negative 0.5, y is 2 pi over 3. X is negative 7.07, y is 3 pi over 4. X is negative 0.866, y is 5 pi over 6. X is negative 1, y is pi. So we're going to finish it off with a different concavity. There we go. All right, so domain and range, kind of a typical sticking point for algebra students. If you wanted to pause the video here and try to write down what the domain and range are, now would be a good time to do that. Domain, what are the answers for the cosine function that we can plug into the inverse cosine function? Well, on the graph of y equals inverse cosine of x, our lowest x value is negative 1. Our highest x value is 1. That's inclusive, so we use braces. A good way of thinking of this is for cosine of x, you're never going to have a cosine of an angle that's less than negative 1 or greater than positive 1. When you're looking at thinking back to the last lesson, when you're looking at a graph for cosine, you're not going to be any higher than 1, you're not going to be any lower than negative 1 if you're looking at the parent function. What's the range for the inverse cosine function? Well, let's see. Lowest y value was 0. Highest y value was pi. So there we go. So this is a pretty good review of what we did last time. The function that we didn't talk about as much last time when we were graphing trigonometric functions was tangent of x. So the first thing I want to point out to you, and this is going to be an important identity that we're going to use a little bit later on in this lesson, is tangent of x equals the sine of x over the cosine of x. That's awfully glare. Trying to glare that a little bit less for you. Mysterious hand floating over the table. Okay. So you see that in the, if you had a reference triangle that you were building in the unit circle, here's your angle, here's a point xy. So this length right here is x, this length right here is y, this is your radius. You can think of tangent as opposite over adjacent. So tangent of your angle would be y over x. Well, we know that in the unit circle that we're working with, the y value of any given point tells you the sine of that angle. The x value of any given point on the unit circle gives you the cosine value of that angle. So here we're using, this is totally separate. Here, instead of using theta, we're using x, okay? So tangent of an angle equals the sine of that angle divided by the cosine of that angle. So that's how we're building this table. We're saying for the tangent of negative pi over 2, that's going to be the sine of negative pi over 2, that's negative 1, divided by the cosine of negative pi over 2, that's 0. Okay, big problem there. You've got negative 1 over 0. You're not allowed to divide by a negative number, so that's why that comes out to be undefined. We've also got this value right here for the tangent of negative pi over 3 that my lighting crew didn't set this up well. There we go. So negative square root of 3 over 2, that's the sine of negative pi over 3, divided by the cosine of negative pi over 3, that's 1/2. So if we were to work that fraction out, those 2's in the denominator would cancel. We get negative square root of 3. That's negative 1.73. If you think about pi over 4 or negative pi over 4, that's where sine and cosine are both square root of 2 over 2. It just so happens that at a reference angle of negative pi over 4, your sine value is negative. So those two values are the same. Since the sine value is negative, though, that's why you get -1 right there. This tangent of negative pi over 6, that comes from basically just the reciprocal of the tangent of negative pi over 3. That's 1/2 over negative root 3 over 2. So those values end up, when you work that division of those two fractions out, you get negative square root of 3 over 3 when you rationalize the denominator. So we end up with these values for the tangent of these angles. Then over here in quadrant 1, you end up with the same values. It's just in quadrant 1, tangent is positive because all three trigonometric functions, sine, cosine, and tangent, are positive in quadrant 1. What we're going to look at really quickly is a factoid about the period of a tangent function. Okay, so let's look at the graph of y equals tangent of x. Tangent of x, there we go. Now, if you remember back to our graphing trigonometric functions lesson that we did last week, we saw that the period for a sine function and the period for a cosine parent function was 2 pi. These tangent functions are periodic as well. You'll notice that you've got an asymptote here where the tangent function is getting bigger and bigger and bigger and bigger and bigger, and then it jumps back down here. Well, that happens at negative pi over 2 and pi over 2. Why is that? Because that's where the function is undefined. You end up with vertical asymptotes where your function is undefined. So let's see how far it is from one point on one period to the corresponding point on the next period. Okay, we already saw in our table that the tangent of 0 degrees is 0. So if we trace this function to try to find what point we get right here, we can do that with menu, trace, graph trace. If we put in 2 pi, let's see if the period is 2 pi. 2 pi is right here. We skipped a period. So 2 pi is actually showing us 2 periods. That must mean that one period is pi. Let's try that. Menu, trace, graph trace. All right, so to get from one period to the next period in the same spot, that's a distance of pi. So the period for the tangent of x function is smaller. It's like a little more squished together compared to the sine of x parent function and the cosine of x parent function. All right, so let's come back and fill in our table for the function y equals the inverse tangent of x. We're going to get, so all we're doing is we're just taking these x and y values and we're switching them around. And this would be a fantastic opportunity for you to try to graph these and see if you can guess what the domain and range is. All right, now we're going to have to extend our x values here a little bit. We're going to actually start with the point x is 0 when y is 0. And then we're going to go to when x is 0.577, y is pi over 6. And when x is 1, y is pi over 4. And now we've got to extend this a little bit. Okay, 1.73 is, well, let's say that's 1.6, so about here for pi over 3. All right, so we're going to get this sinusoidal looking curve about like so. We're going to save that thought for a little bit. All right, then when we come back, x is negative 5.77, y is negative pi over 6. X is negative 1, y is negative pi over 4. We're off the grid a little bit here, about here. When x is negative 1.73, y is negative pi over 3. Okay, so we get this coming back here like this. Now, when things are undefined on a graph, what does that mean that you're supposed to do? You're supposed to think asymptote. Okay, so we're not going to plot the x value undefined. That's not a number. That's saying you're not allowed to cross pi over 2 for the y value. You're not allowed to cross. Now we're out of room down here. Sorry about that, but that's an arrow right there that's going to approach but not cross this horizontal asymptote of negative pi over 2. And that kind of conceptually makes sense if you understand how inverse functions work. Here's the graph of y equals tangent of x. What kind of asymptotes do you have? Vertical, okay? To make an inverse function, you just switch everything around. X becomes y becomes x. So your vertical asymptote is simply rotating 90 degrees to become a horizontal asymptote. So the last thing that we want to do here is get the domain and range. Since we have these arrows on the end of our function, that actually means that our domain is any value from negative infinity to positive infinity. What does that mean? That means that the value for the tangent of x can be any real number. It's not like sine or cosine where you can't go above 1 and you can't go below negative 1. So the domain for the inverse tangent of x is any real number. The domain for the range, or so I'm sorry, the range for y equals the inverse tangent of x is you can't go below negative pi over 2. You can't go above pi over 2. And that is not inclusive. We're using parentheses there, not braces, because you're not allowed to actually take on that y value. So there's the inverse functions for sine, cosine, and tangent. We've got our table. We've got our domain and range. We've got our graphs sketched over the appropriate domain. Here's a nice graphic, courtesy of Miss Cusis. Thank you, Miss Cusis. That we can't see right now. Technical difficulties. Hold on. Ah, there's the graphic. Thought that was the graphic. Now there's the graphic. Okay. So for here's the unit circle. What domain can you use for inverse sine? You can use any angle from negative pi over 2 to positive pi over 2. What angle can you use in the domain for the inverse cosine? Any angle from 0 to pi. What angle can you use for the graph of inverse tangent, any value from negative pi over 2 to pi over 2. So these are the angles that you can use to evaluate inverse sine, inverse cosine, and inverse tangent. So we're going to use those values, those angles that are your possible answers when you evaluate an expression using inverse sine, inverse cosine, and inverse tangent. So let's look at number 10 on your notes. Okay, so it says, use your knowledge of the unit circle and the ranges of the inverse trigonometric functions to find the exact value of each expression without using the calculator. All right, so let's start here with part A, inverse sine of 1/2. Okay, let's think, where are all the places on the unit circle where sine is positive 1/2? Well, we know that sine is 1/2 when the reference angle is 30 degrees. That's pi over 6. Okay. We also know if we think about our quadrants, all students take calculus, right? I switched that up. All students take calculus. That's really hard with your thumb. So all students means sine is positive in quadrant 1 and quadrant 2. So we could use either pi over 6 in quadrant 1 or 5 pi over 6 in quadrant 2, but we need to think about the domain and range for the inverse sine function. The domain is -1 to 1 inclusive. Okay, that's good because we're plugging in an x value of 1/2 right here. What is the range? The range is from negative pi over 2 to pi over 2 inclusive. Okay, so out of those two values that we thought about, pi over 6 and 5 pi over 6, which values are in that range that we just wrote down there? Well, 5 pi over 6 is bigger than pi over 2. Disappointing. We don't get to use that as the answer. So the answer that we're going to use here is going to be pi over 6. When you're evaluating an inverse sine or an inverse cosine or an inverse tangent expression, you're only going to have one answer that's in the appropriate range for your inverse trig function. All right, so let's do an inverse cosine and an inverse tangent. I'll leave the rest of these for you to work out and then check with the notes that your teacher is going to post. Cosine inverse of square root of 3 over 2. Okay, let's see. Cosine has a value of square root of 3 over 2 at 30 degrees. Okay, so that's actually the ordered pair. Square root of 3 over 2, comma 1/2. So let's see, all students take calculus. Cosine is positive in quadrant 1 and quadrant 4. Easier when you're using your 4 fingers, not your thumb, right? Okay, but let's think about the domain and range for the function y equals cosine inverse of x. The domain is -1 to 1. Hey, that's great news because the square root of 3 over 2, that's 0.866. That's inside this domain. What's the range? What possible answers can we get? Anything from 0 to pi. That's helpful because let's see, cosine is positive in quadrant 1 and quadrant 4. So quadrant 1, that would be pi over 6. A reference angle of pi over 6 in quadrant 4, I could think of that as negative pi over 6, also 11 pi over 6 if I rotate from the x-axis all the way around into quadrant 4 counterclockwise. No negative values are allowed, and 11 pi over 6, that's way bigger than pi, so we're going to use the answer pi over 6. There we go. All right, so let's think about inverse tangent now. My guess is that this one looks a little scarier to you than this one, so we're gonna think about this one, okay? So all we're gonna do is revert back to our table that we had for tangent of x. Okay, this is saying, this is, in math speak, this is evaluate the expression inverse tangent of negative square root of 3, okay? That's math people speak for if the value of tangent is negative square root of 3, what angle are you at in the unit circle? Okay, so negative square root of 3, it looks like if x is negative pi over 3, y is negative square root of 3. As a decimal, that's negative 1.73. All right, let's check that in our table. When for y equals tangent inverse of x, right? When x is negative root 3, the y value, the angle in the unit circle is negative pi over 3. So that's the value that we're going to use for the answer to that inverse tangent expression. Let's just double check that against our domain and range that we said we were going to use for the inverse tangent of x. So y equals inverse tangent of x equals negative infinity to positive infinity. It's really hard to be outside that domain, right? Because that's all real numbers. This isn't an imaginary number. We're good to go. What's our range? Negative pi over 2 to pi over 2. All right, we actually do need to check that. Negative pi over 3, that is bigger than the lower bound. It's smaller than the upper bound. We are safe. Whew. So what is the rest of this? I'm going to leave B, D, and E for you to solve. Check with the notes that your teacher puts up. This is using your calculator to check those. As long as your calculator is in radian mode, you should be good to go there. Those answers will be posted. Another thing that your teacher has put up for you on Google Classroom is this inverse trigonometric functions set of notes. Practice those, check the answers against what your teacher puts up, and let them know in class or in office hours or on Remind or somehow if you have a question about it. All right, we're going to switch gears here in just a second. If you'd like to pause the video and jot down some notes, then you go for it. So before we look at solving trigonometric equations, which is the big goal of where we're going with this, we're going to look at compositions of trigonometric functions. We've done compositions of functions earlier this year. That's taking one function and plugging it into another function. So this is basically the same thing that we've been doing in looking at the basic inverse trig functions and just putting it together with what we learned about last week and what we did before spring break with the unit circle. So we're going to look at 3 problems here, and then we're going to post the rest of these for you to review and help you on the assignment. So we're going to look at number 14, we're going to look at number 9, and we're going to look at number 10. So 14 says the arc cosine of tangent of pi over 4. Okay, arc cosine is just a different terminology for the inverse cosine. So we're going to rewrite this problem like this. Okay, so just like we did when we were learning about compositions of functions, you want to work from the inside out. This is saying find the tangent of pi over 4. Then once you know that answer, find the inverse cosine of the value that you get in here. So if you know your unit circle, this is really very, very easy. It's just like a two-step problem. Okay. Tangent of pi over 4. Pi over 4, that's 45 degrees. That's in quadrant 1. If I've got my unit circle memorized, I know that that's the square root of 2. Oh, I'm sorry, that's the square root of 2 over 2 for sine. It's the square root of 2 over 2 for cosine. So since tangent is sine of x divided by cosine of x, and the sine and cosine values are equal, tangent there is 1. The tangent of pi over 4 radians is 1. Now, this is telling me to find the inverse cosine of 1. That's math speak for if the answer you get when you evaluate cosine is 1, what angle are you using? Well, cosine is 1 on the positive x-axis. What's the angle for the positive x-axis? It's 0. So that's the kind of two-step thinking that you want to use whenever you're doing a problem that's a composition of trigonometric functions, from the inside to the outside. So we've got some inverse cosine there. Let's do some inverse sine on number 9. This says find the arcsine of the cosine of pi over 3. Well, that means we're going to do the inverse sine of the cosine of pi over 3. So now it's unit circle time again, right? Pi over 3, that's quadrant 1. Pi over 3, that's 60 degrees, so I'm closer to the y-axis than the x-axis. That's the 0.1/2 comma square root of 3 over 2. So since I'm using cosine, I want to do the x value of that point. So the cosine of pi over 3 is positive 1/2. Inverse sine of 1/2 means if I have an angle and the sine of that angle is 1/2, what angle is it? Well, let's see. That would be 30 degrees for pi over 6. Easy, right? If you know your unit circle, life is just a bowl of peaches. I don't know if that's an expression. Life is a bowl of cherries. Life is a box of chocolates. Know the unit circle. Okay, so now we're going to do one where it's a little bit different now. The first problem that we're going to solve is an inverse trig problem. Cosine of the inverse tangent of square root of 3. Well, let's see, that table that we made earlier can come in pretty handy here as well. When the tangent ratio is the square root of 3, what angle are we using? All right, let's see. For tangent of x, if the answer is the square root of 3, the angle is pi over 3. We can see that in the inverse tangents table that we have over here. When our input is the square root of 3, our y value is pi over 3. And so that means that the inverse tangent of the square root of 3 is really pi over 3. But now we want to find the cosine of pi over 3. Let's see, that is, we actually already did that, right? The cosine of pi over 3 right up here was 1/2. So that is indeed the answer to this problem. So we've built all the way up to this. Now that we feel hopefully pretty comfortable with evaluating inverse trigonometric expressions, we're going to use that to solve trigonometric equations. We're going to go to the last PDF in the notes that your teacher posted and that is solving trigonometric equations. Before we do that, if you want to pause the video and jot down some questions to ask your teacher, now is the time to do that. All right, so we're going to look at some of these problems in the solving trigonometric equations notes that you have there. So we've got an equation here. Cosine of x equals the square root of 2 over 2. And when it says find the general solutions to that equation, that doesn't just mean find one solution. That doesn't just mean find two solutions. It means find all solutions. And you might think, that doesn't sound like a big deal, Mr. Schmitzius. That sounds really easy. Well, the only problem is, if you look at this graph up here, here's a graph of cosine of x, okay? Here, this line right here represents, it is the square root of 2 over 2. That's about 0.707. Okay, see how it's tucked a little bit underneath 1 right there? So you say, man, this is easy. Come on now. Cosine of pi over 4 is the square root of 2 over 2. Hey, that's true. Congratulations, you're right. But remember, this is a periodic function. This goes, there's arrows on here, so it goes forever. So I can go backwards 2 pi. Pi over 4 minus 2 pi is negative 7 pi over 4. That gives me another solution. Go back another 2 pi. Go back another period. That's another solution. Go back another period. That's another solution. Go back another period. That's another solution. So yes, that's right, that pi over 4 is one answer, but that's not the only answer, okay? And then you might also think, hey, all students take calculus. Quadrant 4, cosine is positive. What's the angle in quadrant 4 where the cosine value is the square root of 2 over 2? Well, that would be negative pi over 4, right? You can see that right here, negative pi over 4. Well, I've got the same problem because if I start at pi over 4 and if I start at negative pi over 4 and I add 2 pi, now I'm at 7 pi over 4. And I could add another 2 pi and be at 15 pi over 4. And I could add another 2 pi and be at 7 pi over 4. Plus 2 pi would be 15 pi over 4. Plus 2 pi would be 23 pi over 4. And I could just keep on going forever and ever. So I want an elegant way to be able to write out all the solutions of this equation. Well, there's a two-step process to doing that. First, you want to find your solutions in the domain of 0 to 2 pi. 0 inclusive, 2 pi exclusive. So we can just see that from the graph. That's x equals pi over 4. And we've also got another solution over here at 7 pi over 4. The reason we don't want to use the negative pi over 4 solution is because that's outside of that domain that we want to use. We wanted to go from 0 to 2 pi. So we already talked about the general strategy for finding every solution. It would be take your first point, take your first solution, pi over 4, add 2 pi. So there's going to be another solution here at 9 pi over 4. Add another 2 pi, 17 pi over 4. Add another 2 pi, 25 pi over 4. I don't know about you, but I don't really want to take the time to list all of those out individually because there's infinitely many of them. So we could spend the whole rest of our COVID-19 at home time, plus all of summer vacation, and still not be done unless we figure out a way to do this intelligently. Well, the intelligent way to find all the solutions would be to say, okay, I've got a basic solution at pi over 4, but then instead of saying, okay, add 2 pi to that, and then add 2 pi again, and then add 2 pi again, and then add 2 pi again, we're going to say add 2 pi times k. Now, what kind of number does k have to be in order for you to go around and end up with a coterminal angle. Well, we did this before spring break, right? For coterminal angles, you want to add a multiple of 2 pi. That's a multiple of 2 pi. This needs to be some kind of whole number. It can be positive, it can be negative. If you make it 0, then you'll just get back to pi over 4 that you started with, right? So it needs to be an integer, right? So that's one way to get a solution. Another way to get some of the solutions. The way to get the other part of the solution set would be 7 pi over 4 plus 2 pi times k, where k is an integer. Okay, so we're going to do some practice problems now using this here handy unit circle. Sine of x equals -1/2. So we want to find the general solution for that equation. Well, let's see. Sine is negative in quadrant 4 and quadrant 3. So where the sine value is -1/2 and cosine is √3/2, that's here at, we're going to call that 11 pi over 6, since we want to be on that domain from 0 to 2 pi. And it also happens here at 7 pi over 6. Same ordered pair, except the cosine there is negative. All right, so step 1, what are the solutions on the domain from 0 to 2 pi? That would be x equals 7 pi over 6 and x equals 11 pi over 6. Pretty easy. Now to turn that into a general solution, it's going to be x equals 7 pi over 6 plus 2 pi times k. And we can also get solutions by letting x be 11 pi over 6 plus 2 pi times k. Kind of a shorthand way of saying that a number is an integer is to say that it's in the set of all integers. So we can say that k is an element of the set of integers, which is z, is superscript z. All right, last one before we move on is the tangent of x equals the square root of 3. So let's see, where does the tangent of x equal the square root of 3? That keeps coming up over and over again. It's at our friend pi over 3. Okay, so let's see kind of why that happens. Here at pi over 3, cosine is 1/2. Sine is the square root of 3 over 2. So if you take the square root of 3 over 2 and you divide it by 1/2, those 2's in the denominator cancel, you get the square root of 3. Okay? So x is going to equal pi over 3. But to turn that into a general solution, we need to add the periodic solutions, right? Every time we travel another period for the graph of tangent of x, we're going to get another solution. But remember, the period for tangent is different than the period for sine and cosine. For sine and cosine, the period is 2 pi. We saw that for the tangent function, the period is pi. So we're going to write out the general solution like this, where k is an integer. So that's you've done it. You've solved a trigonometric equation, all right? It's just like solving a normal equation. It's like solve the puzzle, right? What angle goes right here? Now, they're not always going to be this easy. As you can see, we've got some fancier equations that we're going to try to work through. So it says to solve some trigonometric equations, it's helpful to think of the steps you might take to solve a similar algebraic equation. The reason those problems that we solved on the last page were so easy was it was just sine of this angle equals this number, okay? Think of it like a one-step algebra equation. What's easier to solve? 2x equals 8 or 2x squared minus 4 equals 12. Well, it's easier to solve the one-step equation. Our goal is going to be to get these down to easy little one-step equations after we make this way less blurry. I'm so sorry about that. There we go, okay. So we've got this first example. 4 times the cosine of x plus 9 equals 11. We're going to solve this trigonometric equation over the interval from 0 to 2 pi. Well, if we think of cosine of x as like the variable that we're trying to solve for, that's a lot like the algebraic equation 4x plus 9 equals 11. So we're going to solve these two equations kind of side by side, okay? This one's easier to solve, so we're going to solve it first, okay? You guys are all good at math. You're an 80-minute math, so I'm not going to patronize you with the questions about what the opposite of adding 9 is. That's subtracting 9. So now we've got 4x equals 2. So we're going to take 9 away on both sides here. So 4 times the cosine of x equals 2. Okay. We want to get x by itself. The opposite of multiplying is dividing. So now we've got x equals 2/4. 2/4 is the same as 1/2. So when we divide both sides by 4 here, now we've got cosine of x equals 1/2. So let's see, now we've got to think about the unit circle. Where on the unit circle do we have a cosine value that's 1/2? Well, let's see. Cosine is positive in quadrant 1. All students take calculus, quadrant 4. So in quadrant 1, that happens with a reference angle of pi/3. And then you say, oh man, this is so easy. Quadrant 4, I can just make it negative pi/3. Well, not so fast, because you want your domain to be from 0 to 2 pi, 0 inclusive to 2 pi exclusive. So negative pi/3, the coterminal angle, if you add 2 pi to that, would be 5 pi/3. There you go. So easy peasy. Just think of it like a two-step algebra equation. That one is nothing too crazy. The next one's going to be a little bit trickier because it's going to involve factoring. Ooh, factoring trinomials. So we've got sine squared x plus sine of x equals 0. We're trying to solve that over the interval from 0 to 2 pi. Well, just like we treated cosine of x like x to get the algebraic equation, over here we're going to try to compare sine squared of x plus sine of x equals 0 to the equation x squared plus x equals 0. Okay? So you could think about this like factoring a trinomial with a linear coefficient of 1 and a constant of 0. But honestly, this is probably easier to factor as a greatest common factor of x, right? X times x plus 1 equals 0. So since we're doing like a substitution to make this equation over here where x is the sine of x, this is going to be the sine of x times the sine of x plus 1 equals 0. Okay. Here's a quick quadratic equation review. When we're solving a quadratic equation and we get it down to two factors multiplied times each other equals 0, why do we always split it into two equations? Well, there's something called the zero product property. which basically says if you have two factors that are multiplied together and that product equals 0, one of these has to be 0, right? They might both be 0, but that's often not the case, right? Like, let's just say if this over here is a billion and x is 0. 0 times a billion is still 0, right? What if we reverse it around? 0 times a billion, that's still 0, right? So as long as one of these is 0, your product is going to be 0. That's why we split this into two equations, x equals 0 or x plus 1 equals 0. All right, so you already got your first solution right here. Subtract 1 on both sides. That's x equals -1. There's your solution set. All right, same thing right here. If the sine of x is 0, then I don't particularly care what this is. It could be any number. This product is still going to be 0. So either the sine of x is 0 or the sine of x plus 1 is 0. If the sine of x plus 1 is 0, it doesn't matter what the sine of x is. This product is still going to be 0. All right, so here we actually have to put on our thinking caps a little bit more. From this equation, we need to think, okay, on the unit circle, on the domain from 0 to 2 pi, where are all the places where the sine of that angle is 0? Well, that can happen at x equals 0. The sine of 0 is 0. That's the positive x-axis. Okay, what's the other place where sine is 0? Well, sine is 0 on the x-axis. It's 0 on the positive x-axis. That means that it must be 0 on the negative axis too, right? What's the angle on the negative axis, negative x-axis? That's pi. So x can be 0 or x can be pi. And let's see, we also need to think about how to solve this equation. If we subtract 1 on both sides here, then we're going to get the sine of x is -1. Okay, this is a little bit easier. There's only one place where the sine of x is -1, and that is at the negative y-axis. That's 3 pi over 2. So then your final solution set would be x equals 0, pi, or 3 pi over 2. All right, okie dokie. We're going to solve one more together. Here are some helpful hints for you. You can do example 4 and practice C with a greatest common factor factoring. I would just recommend first making it so that it doesn't look like you have your glasses off. There we go. First, make it to where you have a 0 on one side of the equation. Okay, so take tangent of x, move it over, then do a greatest common factor kind of thing. Do the same thing with this term that's on the right-hand side of the equal sign. All right, so let's solve example 5, and then we'll call it quits for right now. So this is 3 times sine squared of x minus sine of x minus 2 equals 0. This sine squared of x, that's sine of x times sine of x. The reason we put the exponent right there is because we don't want to make it look like we're doing the sine of x squared. We're doing sine of x times sine of x. That's the notation for that. So the corresponding algebraic equation that we would use would be 3x squared minus x minus 2 equals 0. Okay, so let's think about how to factor this, and then that'll give us a clue for how to factor this over here. Okay, so it looks like we're going to need to have 3x times x. That'll give us our 3x squared. Okay, let's see. We need two numbers here that are going to multiply together to give us -2. Fortunately, this number is pretty small. We know that we're going to do 2 times 1. We just need to decide which of those is going to be negative and where we're going to put the 2 and where we're going to put the 1. Okay, so we want our sum to be -x whenever we add our inner term and our last term. So we can get a -3x out of 3x times -1. If we put a +2 right here, that would be 2x. So -3x plus 2x is -1x. That's exciting. So that's going to give us the corresponding trigonometric equation over here. 3 times the sine of x plus 2 times the sine of x minus 1 equals 0. And I'm going to leave it there for you. Try to solve out this equation. Set it up just like we solved the previous example, example 3. Take both of these equations, set them equal to 0. You should be in good shape there. Thank you guys so much for your hard work, for your attention. If you or your family need anything at all, if you need emotional support of any kind, reach out to somebody, let somebody, myself included, your 80-minute math teacher included, know we're here for you. We miss you guys. We hope that you're doing well, and we'll see you in online class soon. Thank you.